First of all, thank you very much to the organizers to give me the opportunity to present one of my projects today. And I would like to talk about a project in collaboration with the campus HSE called the optimal convergence rate in the quantum Zeno effect for open quantum systems in infinite dimensions. So let's start. Let's start with a short overview over my presentation. I will start with a short motivation of the quantum Zeno effect in general. It starts already on the left-hand side. Then I will give you the basic setup for to formulate our results. Then I will continue with the results and some proof sketch. And finally, I will sum up and state some open problems and questions which we weren't able to solve yet. Okay, let's start with the motivation. On the left-hand side, you can see kind of an arrow flying to a target. And this is kind of the motivation, or not the motivation, but where the name comes from. So why it is called, the effect is called Zeno effect. And this picture depicts the Zeno paradigm, which is a paradox against the plurality of time. So that, okay, Zeno was a Greek philosopher, and it was a paradigm because if you observe the arrow in each moment, then there's no velocity. So he implies that the arrow would never be, cannot fly, which is a paradigm at the end. But okay, what does this have to do with our project? So in 1977, Misra and Sadashen published a paper, and in their abstract they wrote that an unstable particle which is continuously observed to see whether it decays will never be found to decay. What does this mean? It was it is a theoretical paper where a particle is kind of affected by time evolution. This time evolution is described by a Hamiltonian H, and then we measure this particle after time t/n within PVM, so projective valued measurement, which is described by a projection. So these two elements here. So, and what they have shown is that they looked at this sequence here, and they proved that this converts to this dynamic. So we have a semigroup again, and the generator of the semigroup depends on H, so the Hamiltonian from the time evolution before, and on P. What is interesting is that if we look at the tracer, we apply Born's rule. So we want to calculate the probability that the particle is after the sequence of measurements and steps of time evolution. We want to calculate the probability whether it has decayed or not. And what one can see by, okay, the P commutes through, and the probability of the trace that we can kind of commute the operators from left to the right, we see that the probability is the same as the probability that the particle at the beginning is decayed or not. So which means kind of there's no influence of the time evolution anymore. There's kind of the theoretical result they published in 1977. But of course, there's a question whether this is just a theoretical result or a really provable with an experiment. So, and the experiment came out in 1990 by Itano et al. And they were able to prove or to construct an experiment in the lab which shows that the quantum Zeno effect is kind of real. So, okay, so these are kind of one of the most important results in this big area of the quantum Zeno effect. Of course, there are many other publications, but I will pick out two more, which are quite close, which are closely related to the project, and I will present today. So one of those works is in collaboration with Michael Wolf from 2019, called Quantum Zeno Effect Generalized. And in this work, we generalize this sequence or this convergence here above from Misha and Zadashen to more general, not only measurements, not only PVMs, not only POVMs, but just quantum operations. So we need a few assumptions on an operator M here. And we extended this to from closed quantum systems to open quantum systems and to infinite dimensions. But we still have a generator of the semigroup, which is bounded. And then last year, Becker, Data, and Salzman generalized this result more in several ways. So on the one hand side, they looked at more abstract setup, which we will use in this presentation as well. So it's not important anymore that we have this Hilbert space structure and that this is a measurement and or a quantum time evolution. It's just important that we have some properties on a contraction operator on a Banach space, and we have a semigroup with some assumptions on the generator, and they also allowed for unbounded generators. So, okay, let's go on to the setup. So what do we have? We have this contraction operator M and the semigroup. So we assume we have a Banach space, this contraction. Then we have also the generator of a strongly continuous semigroup, so possibly unbounded. And yeah, with those properties here. And the aim of this talk and also of our project is to give or to prove, first of all, the convergence of this sequence, and also a convergence rate. And this convergence rate is optimal at the end. And of course, we want to weaken the assumption on M and the generator. Okay, let's start with our first result. So our first result focused more on weak assumptions on the generator. So what do we have? We have our contraction, and this contractions must satisfy this assumption here. So we call it kind of a power convergence assumption in a uniform topology. So kind of it is clear that we need a similar assumption like this, because, for example, if we plug in an identity for not an identity, a zero for the generator, then there's just m to the power of n left, and this should converge. Of course, and we will see in the open problem discussion later on, that it would be nice to weaken this assumption further in the strong topology, that we do not need this uniform topology here. But if we are in the uniform topology, this is the best, or almost the best we can do. In the next theorem, we will see that we can improve. Okay, and then we also need an assumption called the asymptotic Zeno condition. And this is defined by those two kind of Lipschitz continuous assumption, also in the uniform topology. And finally, we need that PLP is well defined more or less as a generator. Otherwise, the Zeno dynamics wouldn't be well defined, or which we hope to get. So, and our result or our theorem shows that we find this upper bound here. So first of all, what is important? It is important that we have a 1 over n convergence, and one can show that this 1 over n convergence is optimal. Moreover, we have this C constant, which is explicit. So in our proof, we construct this constant, and lately there were a paper which already used this because it seems to be not that bad, the constant. And then we have some dependencies on LP, and LP squared and LP and X. Okay, so let's go on to the proof sketch. So the proof is splitted in 3 parts. So kind of we add and subtract those these terms, and then we upper bound all these 3 differences. So what we have done for the first term, so equation 3, we use a counting method, which is quite similar to a method used by Burkhardt et al. In 2020. And the rough idea is to split M into MP perp, where P perp is 1 minus P, identity minus P, and into MP, and one can show that MP is equal P by the uniform power conversion assumption. So, and then we expand the exponent here and partition certain terms which converge quite similarly, and then at the end one can show that the all terms together converge with the conversion rate 1/n, and of course we use there our assumptions. The next step is with respect to the convergence rate, the most important one. We use general square root lemma, or we use a modified version, and I will show you why. So first of all, general square root lemma for a contraction C is the following lemma. So it gives us this upper bound here. So it's kind of C to the power of n can be approximated by this semigroup, and we get this upper bound here. And in our proof, we see is a vector value map which converges for n to infinity with a convergence rate of 1/n to the identity. So this part here for n to infinity converges with 1/n. If we plug this in, we have 1/n here times the square root of n. So we just would get 1 over square root of n, which is not 1 over the convergence rate 1/n, which we would achieve. So what we have proven is a kind of a modified Chernoff lemma with the following upper bound. Okay, there's a 1/2 missing, but doesn't matter. And it seems to be worse at first because we have an n here. But if we plug in this 1/n for the C minus identity here, then we see, okay, we have a 1/n squared in the norm times n, so 1/n conversions, which is the conversion rate we need. However, there we have to be careful because we are in a strong topology, and we have to be careful that we really get a 1/n squared here, but with our assumptions possible to prove. Okay, this is kind of also one of the main differences to the proofs before and the theorems before, which kind of enables us to prove this optimal convergence rate. Okay, then the last step is, I would say, kind of second derivative, but we have to be careful because we have unbounded generators. So the idea is that if we would have bounded generators, so if L is bounded, we can expand this e to the 1/nl term to identity plus 1/nl and so on. And then you see, okay, the second term, the second term cancels with PLP, and the third term gives us this 1/n convergence which we need. However, we are not in a bounded generator case, so we have to be careful a little bit. And we prove, therefore, or we use generalized integral equations for semigroups. And yeah, this is this equation here. And then you see, okay, now we have to kind of do Taylor expansion to the third term here. But as I told you, one has to be careful, but with our assumptions, it's possible to prove that this gives us a 1/n convergence rate. But as one can guess, we get this LP squared from this upper bound here. So finally, we prove this 1/n convergence result. So the next theorem focus more on the assumptions on M. So what does this mean? Instead of having just one eigenvalue in the unit circle, so before we have 1 times p, so one eigenvalue in the unit circle, we have a finite number of eigenvalues in the unit circle, which looks like this, and which looks like this, and we also have this constant here, so it's a little bit more general. However, to prove the Zeno sequence converged, we need a relatively strong assumption on the generator, which is that ML and L P sigma, where P sigma is just the sum of all Pj's, is bounded. And this also directly answers the question whether our Zeno dynamics is well defined, because if ML or LP sigma is bounded, we can just define the Zeno dynamics by the normal definition of the exponential function as series expansion. Okay, so these are the assumptions, and there we also need one assumption which comes from the proof technique, which is that T must be small enough, so or n large enough. So it's only possible for small t or vice versa for large n. Of course, if we look at this sequence here, if n is large, kind of t can be a little bit large. T can be also a little bit larger. So, and then we can prove this that the Zeno sequence converges to this Zeno dynamics here in the uniform in the uniform topology. So it's not this strong topology anymore; it's the uniform topology. And if we compare this to the result before, it's kind of natural because this LP and LP is bounded by assumption. So, okay, we get the uniform topology and as well this 1/n convergence rate again. So what is the proof strategy here? So the proof strategy is quite similar, I would say. We all as well have these 3 terms, which looks a little bit more technical and are they're quite similar. So, and then we have these 3 terms, and I have to explain what is, for example, Pj T over n is. So the idea we use here, first of all, the problem we face are these finitely many eigenvalues on the unit circle. And so we need another proof strategy because the counting method doesn't work anymore. So what is the proof strategy? It's a proof strategy. I think we use this in the work with Michael Wolf already, and then Beckerdata and Salzman used this in their work as well, which is kind of consider the semigroup as a perturbation. So we have this operator here, which can be reformed as this operator, and then the second term is kind of the perturbation, and if n goes to infinity, this goes to 0. And in the proof under certain assumptions and reformulations of these terms here, one can show that the perturbation, so the second term, goes uniformly, so the uniform topology to 0 if n goes to infinity. And this is quite important, this uniform topology here. Why is this important? The important thing here is that this m, or the assumption m, is the uniform power convergence assumption. This uniform power convergence assumption can be shown to be equivalent to kind of a structure of the spectrum like the picture shows here. So we have separated eigenvalues on the unit circle, and then inside an bounded spectrum. So in this uniform topology of our perturbation implies that we can find in T small enough such that this separation of the spectrum holds true also for the perturbed M. And this is kind of the key point, and it's also the key point why we need this extra assumption in our theorem. So, and then with we can define with the holomorphic function calculus those perturbed eigenprojections, and for example also use the definition of this operator, and gamma is in this sense the abstract sum of all these curves. This
Sorry
is kind
for
of
interruption. You have 5 minutes.
Yes. I have an eye on the time. I will be. The next slide is the sum up slide. So, and then we have the operator Pj defined, and Cj is kind of just a concatenation of operators including this Pj. So, and then in the last step, one have to show that this Pj can be approximated by or how close, depending on 1 over n, Pj is to the unperturbed Pj, and this was proven in the paper by Becker, Data, and Salzman. And then, as before, for the first term, we can kind of use a similar counting method, but combined with the perturbation approach above, below. For the second term, we can just use Chernoff lemma again, and for the last one, we can use this second derivative approach, and in this case, we can even use kind of the normal derivative, because now the operators are not bounded anymore, not unbounded anymore, so they are bounded. Okay, this is kind of this rough idea in this proof, and let's go on to the summary. So what have we proven? First of all, we have we achieved the optimal convergence rate for the quantum Zeno effect, and we give explicit upper bounds, especially for the first theorem, which seems to be also useful in, for example, finite dimensional or in closed quantum systems. Moreover, by our weak assumptions on the generator, so in the first theorem, the Zeno dynamics could be strongly continuous. So this PLP can be an unbounded operator, which is kind of new because before the results, the papers always assume something such that the generator is bounded at the end. Yes, okay, weaker conditions, and then also we have a result with stronger assumptions on the generator, but therefore weaker assumptions on the measurement, so the contraction operator. So, okay, what is left open, or what are questions which we try to solve at the moment? So, first of all, of course, the weaker assumption, and it would be great if one could prove something in the direction that m to the power of n converges in a strong topology to P, and under this assumption, then the Zeno dynamics looks like this, or it converts like this. And then another thing is the time dependency zero semigroups. So in the work in collaboration with Michael Wolf, we proved the Zeno dynamics, quantum Zeno effect also for time dependency zero semigroup. So the generator L depends in this case on T. In this paper, we had bounded generators, so it's kind of quite easy because one can just approximate the time dependency zero semigroups by time independency zero semigroups. And finally, it would be nice to kind of combine our theorem 1 and our theorem 2 in the sense that we allow for theorem 1 these finitely many eigenvalues on the unit circle, and there one open question is kind of related to generalized product formula for projections, or in this equation, the kind of first step in this direction, yeah, which is kind of the key thing missing here to prove this. Okay. Then thank you very much for your attention, and please feel free to ask questions.